Good afternoon, everyone. So we are going to study integral transform method in this lecture. As I told you that in the last lecture, I told you to write down all the formulas of the Laplace transform, right? So here we are going to solve the integral equation with the help of Laplace and Fourier transform, right? So here you can see the integral transform methods are very convenient in solving the integral equation. That means we are going to use now integral transform method, that may be Fourier transform or Laplace transform, right? So starting with the Laplace transform, we know the definition of Laplace transform which we have studied in the BSc. Laplace transform of f of t is nothing but f bar of p, right? Laplace transform of f of t is f bar of p, which is written as integration 0 to infinity e raised to minus pt or e raised to minus st f of t dt. Some may write it as e raised to minus st or e raised to minus pt. And these are what the list of formulas which we are going to use or which are useful for our integral equation. Okay. The Laplace transform of 1 is 1 upon p, or we can write it as 1 upon s, because some of the teachers teaches as 1 upon s or 1 upon p. Okay. Now Laplace transform t raised to n is n factorial upon p raised to n plus 1, or you can say it is gamma n plus 1, because gamma n plus 1 is nothing but n factorial. And here as what is a condition, n is a positive integer, and Laplace transform of e raised to at is 1 upon p minus a. Laplace transform of sine of at is a upon p square plus a square. Laplace transform of cos of at is p upon p square plus a square. Laplace transform of hyperbolic sine is a upon p square minus a square, or hyperbolic cos p upon p square minus a square. And what is this j naught of et? I hope you are remembering the first uh, semester in which differential equation we have studied, in which we have a Bessel function. Okay, those who don't remember, go back to your first semester differential equation paper and Bessel's equation, in which you can come to know what is j naught of t and jn of t, and Laplace transform of those it is written here. So these are what the formulas which we are going to use. Okay, next one is as I told you in the last lecture, you have to write down all those formulas and the properties. Linearity property of a Laplace transform, L of C1 f of C1 f1 plus C2 f2 is C1 L, or you can write it as C1 f of f1 of s, C2 f of s, right? So these are the list of formula, second translation, unit speed, and then Laplace transform of derivative and all. Next is how to find out multiplication, division by t, and these are what the list of inverse Laplace transformations. Okay, simply the reverse one, whatever the table I have shown you here, the reverse table we have to write here. Inverse Laplace transform is also defined. I hope everyone is knowing what is Laplace transform, what it is converted, why the transformation is needed. Uh, so these are the basic things which you should know. What are the properties of inverse Laplace transform and all. I'm not going to repeat. These are what convolution property f star g, right? And next one that we are going to study is the things we are going to study from here. Consider the Volterra integral equation of first kind. We are going to study the Volterra integral equation of first kind. Why it is Volterra? Because upper limit is variable. Why it is first kind? Because your g of x is 0, and we are going to consider f of x is 0, so that's why it is homogeneous, right? Where k of t of minus x depends on the difference t minus x. What is L of y? It is y bar of t, that is Laplace transform of y. And L of k means Laplace transform of k. L of f means Laplace transform of f. Okay, so now we are going to apply L for Laplace transform to equation 1. And then afterwards we are going to apply inverse Laplace transform so that we can solve our given integral equation. Okay, this is general type of integral equation we are going to solve. So applying a Laplace transform to both sides of our equation 1, we result in this type of equation. And then afterwards, as I told you, we have to apply again inverse Laplace transform by writing the equation in terms of y of. Okay, after writing the above equation in terms of y of t, apply the inverse Laplace transform and you will get the result. Okay. So these are the things we are going to study in the Laplace transform and Fourier transform methods for solving the integral equation. Okay, you can go for these formulas. Now let us go for examples. Solve the Abel's equation. This is what an Abel's equation. It may be there for your MCQ examinations. Uh, this is what the equation introduced by Abel's. What is an equation? Integration 0 to t y of x dx divided by t minus x raised to 1 by 3 is equal to t into 1 plus t. Okay, now we have to solve this integral equation with the help of Laplace transform method. Now just now I told you how to solve it. First you have to apply Laplace transform to our given integral equation and then write the equation in terms of y of p, and after writing it, the equation in terms of y of p, you have to apply inverse Laplace transform, and then you can find out the solution of our equation. So what is our given equation? It is written. Now applying the Laplace transform to this equation, what it will be converted y of t into t raised to minus 1 by 3. Okay, so as it is we are applying for Laplace transform, we are going to consider only t, right? Just like our convolution type of a kernel. As I told you, here we have a convolution type of a kernel. I hope you remember convolution kernel. Here you can see inverse Laplace transform is there. T minus x, instead of t minus x, simply we have written here f into g star. Okay, f star f into g, f star into g. That means f into g we have written. Similarly, we have to do the same thing for this example. After applying the Laplace transform, we have to write it in the form of y star t into t raised to minus 1 by 3. Instead of t minus x, we have to remove x and we have to write the equation. And this t plus t star. Okay. Applying the Laplace transform for this equation, we can write it as L of y of t, L of t raised to minus 1 by 3, L of t plus L of t square. So here we haven't applied Laplace transform. Simply we have written this equation in the form of convolution type of a kernel f into g or f star g. Okay, using the convolution kernel, we have written this. You can see here using the definition of convolution kernel. After that, we have to apply the Laplace transform, and then Laplace transform of y of t, we have to keep it as it is. We don't know what is y of t. What is t raised to minus 1 by 3? We have to apply the definition gamma n plus 1 divided by t raised to n plus 1. And what is Laplace transform of t? 1 upon p square. Laplace transform t raised to 2, that is n factorial divided by t raised to n plus 1. And applying those, simply the formulas of Laplace transform, we get the equation in terms of L of y of t. After getting the equation in terms of L of y of t, now in this step we have to apply the inverse Laplace transform. Applying the inverse Laplace transform, we get y of t. Okay, and we know all the formulas of inverse Laplace transform. What is L inverse of 1 upon p raised to 4 by 3? We have to apply the formula and then we can get the result. Okay. So in this way, we have to solve the examples of integral equation by using the Laplace transform. So here also we have another Bell's integral equation, which is y of x dx integration 0 to t y of x dx divided by under root of t minus x, which is equal to 1 plus t square. Now we have to write this equation in terms of convolution type of a kernel f star into g or f star g, which is written in this form, and then apply the Laplace transform. You have to write it. Okay, all the examples are very easy. You have already remember the formula of Laplace and inverse Laplace transform. Simply first, in the first step, apply the Laplace transform. We know the formula of L of 1, that is 1 upon b L of t, 1 upon p square L of t square, that is gamma n plus 1. We can write it as gamma 3 divided by p raised to 3, or gamma 3 is nothing but 2 factorial. That is gamma n plus 1 is n factorial. And then using those formulas, and then again if you get the equation in terms of L of y of t, again apply the inverse Laplace transform, you will get the y of t, which is the solution of our given integral equation. Now solve the Volterra integral equation of first kind. Here integration 0 to t y of x y of t minus x dx is equal to 16 sine of 40. Again, we can apply the convolution type of a kernel. After applying convolution type of a kernel, we can write the equation in terms of y of t star y of t 16 sine of 4t. After applying Laplace transform, we can write this equation in this form. And then as L of phi of t, L of phi of t is 2 times, we can write it in the form of a square. Now what is a Laplace transform of sine of 80? Sine of 80 is, it is 4 upon, that is a upon a square plus p square, and the 16 outside as it is. And then again we have written square, taking square root on both side, L of phi of t we have formed, and then applying the inverse Laplace transform, we get a phi of t, which is the solution of our given integral equation. Similarly, many examples are there. Here you can see again, solve the Volterra integral equation of a second kind. So y of t is equal to t square plus integration 0 to t y of u sine of t minus u du. Now it is again given in terms of some another variable u. So don't consider u, simply write the equation in terms of convolution type of a kernel. Whatever you have a integration, that part you have to write in the form of star f star g. Okay, after that apply the Laplace transform. Again use the formulas of Laplace transform. Laplace transform of t square, Laplace transform of sine of t. What is Laplace transform of sine of t? As a is 1, so 1 upon p square plus a square is 1 square. So hence again write the equation in terms of L of phi of t, that is equation number 2. And then after writing the equation number 2, again converted it in the form of a L of phi of t, then apply the inverse Laplace transform, you will get the result. Okay, there are so many examples are there. I will share this notes to you. It was shared to me by Abhijit Patel. As I told you, I don't have the notes of integral equation. So the notes that I have got from Abhijit Patel, I will share you on the Google Classroom. You can take them from there, and you can see the page number also. That is 9.9. That is, it is your chapter number 9. Okay, in the chapter number 9, you can see all this Laplace transform examples. Here, there are so many examples are there. Let us go with this example. Solving this equation, again the whatever there is in the integration part, you have to write in the form of f star g after using convolution kernel. Again applying the Laplace transform. Now applying Laplace transform, use the formula of Laplace transform sin t, Laplace transform cos of t is p upon p square plus 1. And again write the equation in terms of L of phi of t, then apply the inverse Laplace transform, you will get the result. Okay, now here you can see inverse Laplace for applying inverse Laplace transform. First you have to use this p plus 1 raised to 2. It is first you have to take e raised to minus t outside, and then inverse Laplace transform 1 upon p square. What is inverse Laplace transform 1 upon p square? Is simply t, because Laplace transform of t is 1 upon p square. Again, there is one more example. Solve this equation by using Laplace transform. I hope you should write down this all the examples. Here also we can go with one more example, cos of t minus x y of x. Write this in the form of f star g, and then you can solve this. So we can go with many more examples of Laplace transform is there. Then some examples of the Fourier is also there. As Fourier was not for your syllabus, so you can see some of the formulas of Fourier transform here, and we can solve them by using Fourier transform also. Okay, as it is not for your syllabus, you have to go with the formulas of the Fourier transform. Let me start with, here we have the definition of Fourier transform. You can see Fourier transform phi of x is written in the form of pi bar of k, just like our Laplace transform. Instead of L, it is used L of phi of t की जगह गई था f of y of x. So instead of e raised to st, it is e raised to I p x. Okay. So here some of the remarks is given, and then infinite for what is the result for infinite. And some of the formulas are given, linearity property, change of scale property, convolution type of a kernel. So all those formulas you have to remember, you have to write down those formula. So you can see here we have to solve the integral equation by using the Fourier transform. Integration 0 to infinity f of x cos of px dx is equal to 1 minus p 0. It is 1 minus p in the interval 0 to 1, and for p greater than 1 it is 0. Right. Now this we have it is in the form of Fourier transform, cosine Fourier transform. So that's why here you can see FC. FC means Fourier transform, cosine of Fourier transform. There are sine and cosine, two different formulas are there. You can see Fourier cosine transform and Fourier sine transform. Fourier sine transform is written in the form of f suffix to the s. Y of x is the formula is y of x sine of px, and here f suffix to the c. Y of x is y of x cos of px. Here also the same formula is there. You can see here f of x cos of px. That is, here also you can see y of x cos of px. Instead of f of x, it is y of x. So we can write it as fc of p, and then we can write this equation in the form of two different interval, that is 0 to 1, 1 to infinity. 0 to infinity is divided in the two forms, 0 to 1, 1 to infinity, because here the interval is divided in the two, that is 0 to 1 and greater than 1. And then just simply divide the interval and use the formulas of Fourier cosine transform. And after using those formulas, that is, you can see here the integration 0 to 1 fc of p. What is the value of Fourier cosine transform in the interval 0 to 1? That is 1 minus p. Here it is given. In the interval 0 to 1, value of fc of p. You can see fc of p. Fourier cosine transform. Value of Fourier cosine transform. हे जे काय आहे ना, हे फुरियर कोसाईनचा फॉर्म्युला आहे. इथे तुम्ही बघू शकता. Fourier cosine transform, Fourier sine transform. Okay. And then you have to apply this, and then you can write the 1 minus p, and here it is 0. Second interval मध्ये तर value 0 आहे. फक्त हे first interval solve करावं लागेल, right? Then after solving, now you can solve this integration easily. To solve this integration, we have to use a u into v formula. Using u into v formula, 1 minus p as it is, integration of cos s sin p of x, that constant term x as it is within the limit 0 to 1. And then derivative of 1 minus p is minus 1. With respect to p, we are evaluating. And this integration as it is, again, integration of this term is sine, integration of sine is cos of pa minus cos of px divided by x, and hence the result. Now here you can see it is now Fourier sine transform. The value of this I can write it as fs of p. Again, this interval is divided into three different interval. Integration within the limit 0 to 1, then 1 to 2, and now directly greater than 2. Okay, again we have to go with the same consideration. Fourier transform, it is written with 1 up to 1 pi. Okay, these formulas you have to by heart the Fourier cosine and sine transform. And again we have divided in the interval 0 to 1. This is 0 to 1, then 1 to 2, and greater than 2. Again write the formulas. Fs of p. What is the value of fs of p in the interval 0 to 1? That is 1. Okay, 1 into sine p of, then 2 into sine p of x, and in the last interval it is 0. Now just simply evaluate the integration. What is the integration of sine px? Is it minus cos px, and as we are evaluating integration with respect to p, x will be treated as a constant, and hence we get the result. Okay, in the very similar way, you can solve many more examples of the Fourier sine and cosine transform. One more book was given to me from Abhijit Patil. You can see here, this is the formulas of sine and cosine transform. As this actually this book is distance education note, I think, from the Shivaji University. Sorry, Yashwantrao Chauhan, Maharashtra Open University. The notes are integral equation के notes हैं आपके. You can go for page number 255 for this. and you can see many more Laplace transform formulas, properties of Laplace transform, and many examples are there. Go with all the examples. So all the examples you can see. Let us go with for the examples which are given here. Okay. Um, these are the things we have seen. Now we have to solve the integral equation. Now initially it was given in terms of p in the notes which we have seen now. Now it is in terms of s is integration 0 to s e raised to s minus t g of t dt. Okay. Now we have to again write this integration in the form of convolution kernel. Again write apply the Laplace transform. After applying the Laplace transform, you get g of p. Write the equation in terms of g of p. Now here it is given in terms of g of p. आधी आपण काय बघितलं होतं y of t or y of p we have written. And after getting that, we have to apply the inverse transform and then you get the result. Again, here it is given g of s is equal to. Now this equation, this whatever the part is there in the integration, you have to write in the form of convolution kernel. Apply the transform, write the equation in terms of g of p. You can see here integration of s is 1 upon p square. Initially, whatever we have seen, it is in terms of zero integration 0 to t. But here it is integration 0 to s. No doubt, I'm going to share all the notes with all the notes. Then apply the inverse Laplace transform, you get the result. And as I told you that J of S minus T, which we have studied in the differential equation paper, the Bessel's equation. In the Bessel's equation, we have studied the J. Okay, what was the Bessel's equation? You have to remember that. And then apply the Laplace transform. Applying the Laplace transform, we know what is the Laplace transform of J, 1 upon and p square plus 1. And then again apply the inverse Laplace transform, you get g of s is equal to L inverse of this. It is L naught of s. Again, solve the many more examples there for Laplace transform. So all these examples, I hope it is not very important to go with the example because you know what is Laplace and Fourier transform. Many more examples are there. You have to solve all the example, and then we can go for the Fourier transform. Here you can see you have to by heart all these formulas. Fourier transform, inverse Fourier transform. Okay, sine and cos. What is the Fourier transform of t minus f of t minus a? Here formula for this is given. Many more examples are also given for the Fourier transforms. Okay, the same formulas are there, same examples are there. Just now we have solved this example, na? Integration 0 to 1, 1 to 2, and greater than 2. Again, they have divided and then solve the integration within the limit 0 to 1 and 1 to 2 because greater than 2 is 0. Okay. And then after that, we are remaining with the Green's function only. Okay. Thank you.